Good morning, everyone. Good afternoon. Welcome to our third and final for this year webinar series on all things ROCm and how to use ROCm for varying different applications. And today we'll be talking about fine-tuning Llama 3 on the Radeon GPUs. Our hosts will be Garrett Bird and Dr. Joseph Schoonover. Please, during the course of the webinar, if you have any questions, click on the question button, submit your questions. All questions will be answered at the end of the webinar. And we'll have a live interactive session with both presenters, both Garrett and Joe. So with that, again, my name is Bryce Mack, and I'm listed there at the bottom. I want to say welcome to the webinar, and I hope you have a good time. I'm going to turn it over to Garrett. Garrett, it's all yours.
Hello, and good morning. Thank you so much for taking time out of your busy schedules to join us today. As Bryce just said, I'll be talking about fine-tuning Llama 3 on AMD Radeon GPUs. So just a few housekeeping things first. So any opinions that I may express or anything that I get wrong, those are my opinions and my mistakes, and they are not reflective of AMD. Here at Fluid Numerics, we are experimentalists, and we have the belief that 50% of what you know today might be wrong tomorrow, which is certainly true in such an active area of development. And I also want to mention that any links to third-party sites, so as you'll see, like the Hugging Face documentation, AMD is not responsible for the contents of those sites. They're just provided merely as convenience. So let's really get into it. It's always good to motivate things with a question. And so we'll start sort of with the most rudimentary question in this space. What is fine-tuning, at least in the context of large language models? Well, it's exactly what it sounds like. But as you'll see, is sort of the theme of today. It does what it says on the tin. But fine-tuning for an LLM is the process of increasing a pre-trained model's performance for a specific task. So right now, there's sort of all these chatbots, right? Instead of perhaps doing a search query, you have your favorite AI agent that you ask a question to. And even this is an example of fine-tuning. So you have these sort of what you might call general purpose or foundational models. Say Llama3 is a foundational model. And then you fine-tune it. One example of fine-tuning it is specializing it to respond in this question-answer format, right? This sort of student-teacher sort of relationship with it, depending. Of course, another way is actually to just update its sort of domain knowledge. So maybe you have some internal data set specific to something for your company, or maybe specific to a certain scientific domain. Updating it to be more knowledgeable on that data is, of course, another example of fine-tuning. And then also, say you spend all this time developing this model, and you fine-tune it, and you develop it. You go through it. You have this wonderful model at the output, and you don't necessarily want people to ask it maybe how to make a weapon or how to poison somebody. So fine-tuning it away from that is another perfect example of this fine-tuning thing. So covering some more rudimentary knowledge. There's really two main phases in the life cycle of an LLM, right? And many of you might be familiar with this. So we have training and we have inference. Inference is the one, especially if you're not a developer, this is the one that we interact with, I would say the majority of the time. Anytime you provide a prompt to a chatbot and it generates a response, it is inferring which tokens to generate. So it's executing that inference phase. It's already trained. It's just, the model is just running at that point. And then, of course, the phase that precedes that is training, which is exactly what it sounds like. In a more, breaking it down into, say, a more traditional neural network context, right? We have our neural network, and then you initialize it with random weights, either uniformly or normally, whichever, pick your favorite initialization technique. But you initialize it, and then you go through the process of giving it training data, going through backpropagation, executing your favorite training method, right? And then you fine-tune, well, perhaps I shouldn't say fine-tune, you tune these weights, right? Grant Sanderson has this wonderful analogy of tuning a bunch of dials for model parameters. And so conceptually, there might be a bit of balance between this, right? Training, you sort of get it ready to answer, and then inference answers your question. But there is certainly an imbalance when it comes to memory footprint. And now would be a good time to sort of talk about a key assumption of today, and that's that everything is sort of, we're exclusively talking about doing things on the GPUs. You can do CPU offloading and that type of thing, but that is sort of beyond the scope of today. We're just focused on GPUs. And so there's certainly a bit of an imbalance between these two phases. Generally for inference, if you can load the model into your GPU's memory with maybe a little bit of overhead beyond that, you're generally fine to run that model, which is great because, I mean, there are certainly huge models out there, but that's, you know the cost sort of upfront. That's not so bad. With training, on the other hand, going through a quick conceptual checklist, of course, you have to upload your model into memory. So all of these, say for Llama3, right? Llama3 8 billion, you have to load all 8 billion parameters into memory, just like inference. But then you also have to calculate gradients, save optimizer states, apply backpropagation, and not to mention uploading, I should say, to memory, transferring to memory your training data. So like one batch of training data, which depending on what kind of data you're dealing with can certainly vastly increase the memory footprint. And so we face our problem here, especially on Radeon GPUs, right? Because unlike server cards, Radeon GPUs are not necessarily packed with tons and tons of memory, which is totally fine because Radeon cards are not meant to be server cards. But it's fun to push limits, right? And many people are eager to run these models locally on Radeon. And so our problem is in fine tuning, we essentially, if we take a sort of naive approach, we're essentially retraining a model, right? So if we think we have our model, we have our pre-trained weights, they are generally in the right direction for where we want them. But at the end of the day, we have new data, and we're going to have to go through that training process again, which is, of course, as we just discussed, quite memory expensive. So we present a little bit of a naive solution here. Let's just reduce the memory footprint of this training process. Again, it sounds naive, but there are some wonderfully clever techniques to get this done. So I'll also give a warning here. We're about to go down a bit of a rabbit hole in terms of techniques and implementations and acronyms. So I will do my best to be clear as we go exactly where we're at. So in the fine-tuning world of LLMs, there is a sort of class of fine-tuning methods called parameter efficient fine-tuning, or PEFT. And essentially, the core idea of PEFT is that instead of retraining every single parameter of a model, you retrain a subset of these parameters. And the particular implementation, one of the more popular implementations of this, is called LoRA, or low rank adaptation. And essentially what LoRA does is, again, if we go back to an example of a classical neural network, you have several different layers. You freeze all of the pre-trained layers, and then you add what's called an adaptive layer or an adapter layer at the end. So all of your pre-trained weights are frozen, and then this adapter layer is what is fine-tuned. This is the only layer that is trained in one neural network. And then from LoRA, we have QLoRA, which is an implementation of LoRA, which is quantized. And this graphic is taken from sort of the foundational paper on QLoRA, which is Tim Detmer's QLoRA Efficient Fine-Tuning of Quantized LLMs. And essentially what this graphic is getting across is, on the left, we have sort of our naive, it's not necessarily naive, but our naive full fine-tuning setup, where we're using single bit precision, which can be quite costly. LoRA, again, still using single bit precision, but we reduce the footprint here, right? So if we look in the middle, sort of our footprint of our adapter layers are much smaller. And then this particular graphic with QLoRA, it indicates using 4-bit, which is where the quantization comes in. And it's also demonstrating a page detention mechanism with the CPU, but we're not necessarily worried about that part. So I mentioned quantization. What is this, right? It's quite simple. So quantization is just re-expressing or discretizing something in a new way. So we do this all the time, say with real numbers. Of course, the real number line is continuous, and I'm not going to get into different levels of infinities here, but there's infinite number of numbers on the real line, right? But we quantize this to floating point numbers, right? Numbers that we can express with some level of precision that we specify. And we can also quantify floating point numbers to lower precision floating point numbers. So if you think taking 64-bit double precision and quantizing that down to single bit, or as we'll see today, taking a single precision 32-bit floating point numbers and then quantizing that down to half precision 16-bit, or even down to 8-bit and 4-bit. And there is a few different algorithms and implementations out there, and I should be diligent here and say that Torch.io is not necessarily an algorithm; it's sort of a framework for these other things. But I believe all of these are available in PyTorch. But again, one of the more popular implementations, and the one that we'll be looking at today, is called blockwise quantization. Specifically, we'll be looking at its implementation in Python, which is called bits and bytes. And so here's another graphic, again, taken from a paper by Tim Detmers, who is, as far as I understand, the lead developer behind Bits and Bytes. And so this is sort of the breakdown of this blockwise quantization process. So you have an optimizer state, or you can think of it more generally as just a set of floating point numbers. So say maybe a matrix of floating point numbers. We first chunk this into blocks, and we'll motivate this later. But we'll chunk this into blocks, and then in each of these blocks, we'll find the absolute value, the maximum absolute value. We divide by that and normalize it. So then every block in our optimizer state is scaled between -1 and 1, so it's normalized. We then round this to a nearest 8-bit value between -1 and 1. And what I mean by 8-bit value here is if we take the range between -1 and 1 and divide it evenly, uniformly between with 256, so 2 to the 8-bit divisions, then we have this range, right, which we can round and store with 8-bit. And then we index these. So we map each of those rounded values to an index between 0 and 255. So we start out with a single precision 32-bit floating point, a set of single precision 32-bit floating point numbers, and then we can store them as 8-bit integers. So this is quite memory efficient. And then dequantization is just the reverse of this. So we have our index, and then we do a table lookup for the nearest value between -1 and 1. We denormalize, and here also I should mention that there is a little bit of extra cost with this. It's not necessarily 30.32 strictly to 8-bit. There is a little bit of cost because we have to store the scaling values for each block. And so we bring those back in to denormalize them. And so you get approximately, with a little bit of rounding error, you get approximately the floating point values that we started with. And so if we think about how parameters are stored, oftentimes these are stored as, like I just described, matrices, right? Excuse me. So these are stored as matrices. You can think about an embedding matrix, which we'll actually look at later. And it turns out that grayscale images are also matrices of floating point numbers. So I'm doing a bit of pre-processing here on a test image, which just happens to be the album cover for Plastic Beach by the Gorillaz. and I'm just resizing it and then converting it to grayscale. You could really do what we're about to do with color images as well, but you would have to do it per channel, and generally it's much easier. The analogy works much better if we convert it to a rank 2 tensor instead of a rank 3 tensor. So our input image ends up being this grayscale. Again, this is just a visualization, right? And I should also clarify that technically in grayscale images, you start out, they're already stored with an 8-bit bit depth, 8-bit color depth. So we're quantizing it down to like 7-bit, 6-bit. But the analogy works quite nicely from going from 32 to 16 to 8, and so on. And also technically the values they're technically stored between 0 and 1. But we can think about black. If we think back to our blockwise quantization algorithm, we can think about the color black corresponding to -1, and the color white corresponding to +1, and then some gray, a variance of gray in between them. And so if we have this sort of matrix of floating point values, a sort of naive way that we might quantize this is just to round to the nearest value, right? So maybe traditionally, if we go from 64-bit to 32-bit or 32-bit to 16-bit, you just round to which value is nearest in that new format. And that can work, right? It has its trade-offs. You can certainly see the information loss in the graphic as we reduce the bits, especially when it gets really low. But this is sort of what motivates the blockwise condition of quantization, right? So if we do this to the entire image, then we lose a lot of information. So say in our set of data, if for some reason we're quantizing, say, the weights of a neural network, right? Again, with a more classical example, the weights of a neural network tend to be normally distributed. And so many of the values lie quite close to 0. But you'll get outliers, which are further away, which are extremely positive or extremely negative. And so if you scale with these outliers considered and you squash this down to -1 to 1, then the majority of your values, right, in the bell curve, that gets squashed quite near 0. And so you don't really capture the nuance that is going on in that bell curve because these outliers are sort of squashing everything. But blockwise quantization sort of lets these outliers still sort of have their impact because we can't just, again, you're sort of losing information in another way if you sort of like chop them off or discard them in some way. So the impact of outliers sort of still have their effect, but we get much more nuance with sort of the middle values. And we can see this here. So our original input is right in the middle, and our naive approach, so without blockwise implementation, is on the right. If you're familiar with signal processing or image processing, this is just called, this is a form of posterization. And then our blockwise implementation is on the left. And so you can see, say, with our posterized example, we have quite a bit of information loss in the shadows cast over the ocean, right? And even in the sky. It doesn't necessarily look bad. It kind of has a nice stylistic look to it, but there's certainly information loss here. Whereas in blockwise quantization, we get a much more nuanced depiction, say in the water, and then also even in the sky. And even though you can sort of tell where these blocks are being applied, we get a much less information is being lost. And so we can do a bit of a simple calculation here. This is maybe doesn't tell the whole story, but it's a good calculation to do nonetheless. Say, for example, we are looking at the embedding matrix for Llama3. So this comes as 32-bit single precision. And Llama3 has a vocabulary size of about 128,000. And so there's that many tokens in the Llama3 model. And then each token has an embedding when we embed these tokens, the vector embedding has a length of about 4,000 of 4096. And so raw, so to speak, when we factor in the memory footprint of this, the single matrix comes out to be about 2 gigabytes in memory. But if we apply 8-bit blockwise quantization, we follow the same formula here, substituting 8-bit instead of 32-bit. And then here we're using a block size of 4096, which is sort of on the upper end of block sizes in these applications, but it's quite realistic. So if we use a block size of 4096, we have to consider the memory footprint of saving those scaling factors, right? Those denormalization factors. And so that's highlighted in orange here. And even with this sort of simple rudimentary implementation of it, we get a space saving of 0.5. So we essentially cut our memory footprint in half just for this one set of parameters. And I should also mention that the embedding matrix certainly does not tell the whole story in terms of model parameters. There are many, many other things to consider in a model. I think, let's see, a naive calculation, this is just a few million out of, say, an 8 billion parameter model. And so space saving of 0.5, I mean, that's not bad, right? It's actually pretty good. But we can make it even better because we can apply quantization recursively. We don't necessarily have to save our denormalization factors as single precision. We could save them as half precision and so on and so forth. And so there's other ways to increase the memory savings even further. And so what we're going to be looking at today, I want to just touch on the model that we'll be using in the data set. These are both available on the Hugging Face Hub. I'm sure many of you are familiar with Hugging Face. Of course, for Llama, any of the Llama models, you'll have to request permission from Meta, but it's that they're generally very quick to approve people. At this point, I'm convinced that I don't really need to sell you on the Llama3 data set. It's quite, it's probably, I don't know if it's the most popular. It's certainly one of the most popular models out there. And it sort of speaks for itself in terms of popularity and performance. But to give a brief run through of it, of course, it's developed by Meta. It's Llama3 has 8 billion and 70 billion parameter versions. Of course, there is also Llama 3.1 and 3.2, which I believe both of those have 405 billion parameter versions, which is sort of incomprehensibly huge to me. That's a giant model, which is really impressive. For Llama 3, it comes with a context length of about 80,000 tokens, and it scores consistently high on various LLM benchmarks. And it has tons and tons of downloads, and then the vocabulary size and length that we've discussed before. And so we'll be fine-tuning this today with the MetaMath QA dataset. And this is actually unrelated to Meta platforms. But what the MetaMath QA dataset essentially is a set of math questions, sort of on the high school or maybe even early college level, where, as you can see here in this example, right, it's just provided this very basic math question. This isn't one example row. It provides an example math question and then an example response. And so I've been rambling for quite a while. So where exactly are we at in all of this? So if we think out, right, I guess very, very broadly, right, we're in the world of LLMs, but going a bit more specific than that, right, we're focused on fine-tuning. So in the world of fine-tuning, there are various ways to implement this. You could do what's called full fine-tuning, where you retrain every single weight in a model, or maybe you could do some other things. But today we are focused on parameter efficient fine-tuning, where you just retrain a subset of values. And the particular implementation of parameter efficient fine-tuning that we're looking at is LoRa, which is lowering adaptation, which, if you recall, again, going back to our classical neural network example, You freeze the weights in each of the pre-trained layers, and then you append a layer with LoRa, and then you train that. And then QLoRa just applies the sort of quantization techniques that we've been walking through to LoRa to get a lower memory footprint. And so we'll be getting our hands dirty today, but maybe if you don't want to get into the nitty gritty and installing things, I definitely recommend checking out VLLM, which is essentially a toolkit for serving inference to users, as I understand, that implements the paged attention algorithm. You should certainly read, if you want to do a bit of homework, you should certainly read the paged attention paper. Unfortunately, I can't remember exactly what it's called. But VLLM is also presented in that paper, to my understanding. And it just so happens that AMD has just released a Docker image for VLLM using ROCm 6.2, the very latest and greatest. So if you want to just get up and running quite quickly, VLLM is certainly a good way to do that. And if you think back to all of these quantization algorithms that I listed, of course, bits and bytes is just one of them. There are tons of others that I believe VLLM, I can't necessarily say that it supports them all. I'm not certain, to be honest, but it's certainly a good way to explore at least some of them if you want to try out different things and compare. And so with sort of the conceptual level covered, I'll transition now into going over our coding example. So feel free to follow along, maybe if you're watching this in the future, or if you're watching this now and you are very quick to get things set up. All the notebooks and scripts I'll be walking through are available on the Fluid Numerics GitHub, and that's in the AMD ML examples repository. And so if I transition over to this, I'm not going to focus too long on installation, but it is definitely a good thing to mention. So it's already sort of, I guess, the two core pieces of software that I will assume you have installed are ROCm 6.1. This is what I'm using today. And you also are comfortable with Conda, and you have Conda set up, and you have pip installed and all that good stuff. I guess the first, not really tricky step, but the first maybe more involved step is getting a ROCm compatible version of PyTorch, which you can get at this link provided. I'm sure if you just Google install PyTorch, the install PyTorch locally page will pop up. And they have a wonderful configurator tool to get ROCm, to install a version of PyTorch compatible with the version of ROCm you have installed. And again, today I'm using ROCm 6.1. And so sort of the most involved step is installing bits and bytes. So as I mentioned way at the beginning, it shouldn't really come as a shock to anyone to say that this is certainly an active area of research. And so as of me checking at least a few days ago, the main branch of bits and bytes does not support Radeon. However, the AMD ROCm fork of bits and bytes does. Their main branch, which is called ROCm enabled, that does support Radeons. And this is slowly being pushed to a branch on the main bits and bytes repository called multi-backend refactor. But today I'll be using the repository from ROCm. So that's just ROCm bits and bytes on GitHub. And they provide these install instructions in the README. So all the usual things, right? Clone, CD, make sure you have the right branch, install the right things. You will need CMake and make installed, which should be fairly standard. And the only thing that you'll really have to specify is GFX 1100. So GFX 1100, if you're not familiar, this is, of course, the architecture for the higher end Radeon cards, so the 7900s. And at least I know of at least two of the Radeon Pro cards, the W7800 and the W7900. But sort of the upper ends on each of the Radeon lines is GFX 1100. And of course, you can do this with on Instinct as well. It works quite nicely on Instinct. But today we're focusing on Radeon, right? And then the only other things you'll need are the relevant handful of Hugging Face libraries. Of course, Hugging Face is behind the Transformers library, which is sort of the star of the show. But we'll also be using data sets, of course, to actually handle the data set, PEFT to do parameter efficient fine tuning, evaluate to evaluate our model as we train it, and then TRL to do some multi GPU stuff. And then some hanging bits. We will also need scikit-learn, which comes in during the training step, and then Jupyter, because Jupyter notebooks are wonderful. And I also provide a quick script here that outlines acquiring the model and the data set. Again, these are on Hugging Face. I tend to just go ahead and download things locally. But of course, there are APIs and things available in the various Hugging Face libraries for you to pull these things automatically. I like to store things locally. It's easier for me, but you can adjust this however you need to and implement it in your Python code. And so here we go, diving into our notebook here. So this is for training on a single Radeon GPU. Of course, I've already talked about software requirements, the hardware requirements. Yeah, so all of this I've outlined in the install script. We import things. As you can see, I've already run this, so maybe I'll get a chance to run it again if nothing breaks. So what I'm doing in this cell is just making sure that PyTorch, making sure that we have a CUDA device available, and that PyTorch knows that. Here I'm just providing, I already downloaded the Llama3 8 billion model beforehand. Again, you can just run this install script and that should do that for you. So that's installed locally. And then this is where the fun stuff kind of happens, right? In terms of training. I should also mention as well, definitely in terms of inference, or maybe more generally, more of the basic sort of interoperability with the Hugging Face libraries, you should definitely check out the previous webinar where I covered just basically getting started from scratch, getting up and running the Llama3 model. And then this is sort of the next step in that. So if I gloss over any sort of like basic steps, like what a tokenizer is, like why I'm specifying it the way I do, or as you'll see in inference, like the arguments that I'm providing to pipeline, all of that is explained in the previous webinar. So certainly check that out. But if you're familiar with this, I'm essentially telling the model to use the Llama tokenizer here. And then if you're familiar with the Hugging Face world at all, you'll know that sort of configs, config classes, or even config files are the way of the world. And so here we are just specifying what I went over earlier, right? But instead of doing 8-bit quantization, which I mentioned, we're actually going down to 4-bit quantization. So in our bits and bytes config, again, to find out exactly what this is imported from, definitely go to the top cell. So with bits and bytes installed and transformers installed, I can load in 4-bit and set that to true. Here I can also specify to use floating point 4-bit. An alternative to this would be NF4, or normal floating point 4, which was a data type developed in either the QLoRa paper or perhaps Tim Detmer's original optimizer, 8-bit optimizers paper. But it's a really clever data type and you need to read about it, but I'm not going to get into the details right now. This argument is just applies what I mentioned earlier about how we can sort of apply quantization in a nested way. So we are reducing the memory footprint of those scaling factors as well. And then, of course, many cards are not yet equipped to handle these extremely low precision data types. So we have to sort of disguise them as other data types to actually do the computation. And so we're sort of disguising it as half precision here with floating point 16. So I fill out my our config here. And then we load in the model. I'm just calling it quantized model and passing it that path. And then passing that config. And the device map auto is just letting it grab the GPU. And there are really two sample prompts that I've been playing around with. I came up with this, well, I'll let you judge the difficulty of it, but Johnny has 3 apples. Jane has 14 oranges. Jane says that she will trade 3 oranges for 1 apple. What is the maximum number of oranges that Johnny could trade for? And after many research hours, I determined that the answer to that is 9. And so we can see how the model, how accurately it predicts that. This is more of the basic information. Again, I'll allude to the previous webinar. But setting up a pipeline, essentially what we're doing is just saying, use this quantized model that we've specified. We want to use it for text generation. And then we're specifying, of course, that we're using float 16. We're pointing it to the tokenizer, these sort of basic things. And then here we are generating our sequences. And here, okay, so I've actually only specified to return 1 sequence. And I've passed in our sort of Johnny Apples input. And I've also limited it to 512 output tokens because sometimes when you don't train, don't spend a ton of research time training these things, they can get quite rambly. And so this is just putting a cap on it. And I have a few other parameters in here, which I explained in the other webinar. And so let's see what kind of response we have. Johnny has 3 apples, yada, yada, yada. Okay, it seems like it actually just immediately terminated with an end of sequence token. Maybe I should have generated more than 1 sequence. But that's sort of the variability that you get when you don't. This is sort of why we're fine tuning, right? So that we wanted to actually provide an answer and not just immediately terminate. And so we've sort of implemented the quantization half. And so let's go on into considering the adaptive layers. So again, right, the transformers libraries sort of speak in configs, and our LoRa config here, we provided a rank. So if we think about, yet again, if you say all of these layers are frozen and we add our adaptive layer at the end, the rank is how many neurons are in your adaptive layer. And somewhat arbitrarily, I set that to 16. These things tend to be, from what I've seen, either like 16, 32, 64, sort of in that range. So I've chosen 16. LoRa alpha is a little bit tricky to describe. To fully understand it, I actually provide a link to the original LoRa paper where it talks about low rank adaptation. And they go into a bit more detail describing what this is. But you can sort of think about the alpha parameter as being how much do I want this final layer to affect the pre-trained model. And it's scaled where you have your rank divided by your alpha. And from that, you can sort of get that the effect of this. So if we set each to 16, then we get 1/1, and we're fine. It's sort of the default value, which they also mention again in this paper. And then we'll just add a brief dropout layer. In adaptive models, it's quite common to just set the bias to none. Of course, we're using this for causal LM. And you can see what other types of parameters you can pass with the documentation provided. And if you're familiar with the structure of transformer models, because that's really what's going on under the hood, transformer models are sort of, one way to think about them is a few different neural networks doing a few different things. So if you're familiar with like key, query, and value matrices, of course, these sort of represent neural networks. And we're basically specifying which networks we want to append adapter layers to. And here this is, to my knowledge, this is all of them. This is the full list. I'm sure in documentation you can find, or even definitely in the source code, right? You can find an even more complete list. But to my knowledge, this is a complete list. So basically at every possible stage, we're adding adapter layers. So then we just apply this config, and then we go through the usual process of putting it through a pipeline and generating some output. And again, I just generate one sequence. So you will get a warning right here as well. I should mention, maybe we got some warnings above as well. But the PEF model for causal LLM, or for causal LM, this is sort of being the class that the Llama class is being handed off to. But under the hood, we have sort of a Llama model, which is fine for text generation. But in general, PEF models are not necessarily supported for text generation. And that's all this warning means. Okay, it seems like it just terminated again. Wonderful. So keep in mind at this step, right, we're not, nothing has been tuned yet. We've applied the adapter layers, but nothing has been fine-tuned. And so here we will load our data set, and I'm just loading in 100 values sort of for brevity. I don't really want to spend time training it on 10,000 samples quite yet. And then we split it between train and test with 0.2, right? So it will end up with 80 train and 20 test. And then we can just sort of see the shape of our data set here. So in the transformers world, we have these things called chat templates, which is exactly what it sounds like. You can pass it in either from the user or from data. You can pass in, you can format, say, the prompt, which is passed in depending on different fields. And these are actually formatted as Jinja templates, which I'm not super familiar with, but I learned just enough to sort of make a very simple one. For the fine-tuned model, Llama3 instruct, it has this sort of long, multi-line, complicated chat template where it basically says, it puts a token that specifies that the user is speaking, and then it will sort of put in the prompt, and then it will end that and then say that the assistant is speaking. And so you can sort of train it using this particular format and then have a pipeline that takes in responses or prompts from the user and digests it in this way. But it's good to mention that it is there. But for today, I'm just using this very simple one, which basically just appends. So in our data set, again, we have a query and response. It basically just appends these. So it asks the question and then it appends the response. So we're sort of training it to just provide an answer when a question is asked, and not necessarily decorating it with all the chatbot sort of niceties. And so we just apply it here. So we have our data set, and then we map it using this function that we've defined. And this produces a new column, which is just called text. And I print two examples here. So as we can see, what is the largest number of consecutive positive integers? So here's our question. And then it just appends our response. And then same for this example as well. So this is ultimately going to be our training data, right? And so here we just have another example. Yeah, it's just another output example for a query from the test data set. And here we define our metric for training the model. I'm not going to get into the details of what accuracy necessarily is. I definitely recommend you going to this repository and following all the nice links and reading the documentation. Hugging Face has some wonderful documentation, but you can think of accuracy. It's basically exactly what it sounds like. How accurately is it predicting what comes next in the sequence? And so here's a quick loss function to sort of formalize that process. And so there's tons and tons of arguments here, right? And I'll just, for the sake of time, I'll just sort of hit on the key ones. Many of these things, if you've taken like an intro to machine learning class, many of these are should be familiar. Like learning rate is sort of one of these more basic importance, but early learned parameters, as well as number of epochs. I definitely recommend playing with batch size. You may not want a batch size of 1 and 1 for training and evaluation. But I was just trying to get memory as low as possible. And so this is what I was working with. And then I have a nice, I specify the output here. I will say the important one, if I'm going to mention any of them, is this devious FP16 parameter, which I've set to true. And the reason that really needs to be set to true is because in our quantization config, this is our compute data type, right? So this is sort of how it's representing our 4-bit parameters. So FP16 certainly needs to be set to true. Otherwise, things will not work. From personal experience, I please take my advice. And then we pass it to this supervised fine-tuning trainer class, which is, again, exactly what it says. It's the trainer class is sort of Hugging Face's. It's the class used to train things. Big surprise. And yeah, perhaps I'm not doing things quite correctly. There's also an SFT config, which you should be passing to this, and which I should be passing to this, to specify, max sequence length. Again, I'm capping it at 512. And most of this is quite fairly intuitive. Model, we pass it our adapted model, and then specifying the train and test columns, or of that split. And then we're specifying the text column, which is actually going to be the data that we train on. And then it's as easy as just running trainer.train. And of course, I had this tiny sample size of our data set that was just 100 rows. So maybe our training loss is not the best. And it's actually gone up in a step, which is interesting. But as you can see, you'll get this, the typical sort of nice output where you have training steps, depending on what you specify. When you wanted to evaluate, you can change that based on number of steps, based on other things. I just chose to evaluate at number of steps. And you can just save your model with trainer.save. And so I'm not going to run this model because it would probably be insane because of the small data set. So I'll quickly sort of walk through an inference here. This inference notebook is very similar to the notebook that I provide in this. This is available in the repository, but a sort of more explained version of this is available in the same repository, but in the directory for the previous webinar where these things are sort of extrapolated on. And so, okay, here's a good sign, right? The answer is 9. I actually printed out 10 different sequences. So maybe we can do a rough sort of grading here. And again, sometimes if you don't fine-tune a model to respond in this instructional way, you will get kind of these repetitive sort of responses, and there are ways of handling that. But for now, I'm just sort of wanted to respond at all, right? That would be a big step up from previously. And so with in the first iteration, it actually gets the answer right. The answer is 9. Okay, yeah, if you trace through two apples, it even expands on the reasoning a bit. Okay, not bad. The answer is 42. This one seems to be a Hitchhiker's fan. 7, not quite. 11, 4.7. Okay. Okay, we hit 9 again down here. But this is certainly better than getting no response at all, right? Which is what we got initially. So if we think back to Llama 3, Llama 3 is one of these foundational models. It's not necessarily fine-tuned to respond in a question-answer format. So even with this sort of rudimentary run, it's already sort of geared in the right direction. Okay, I got this one right as well. I think we're at 3 out of 10 so far. Okay, 4 out of 10, I think. 40% is maybe not the best, but not bad either, especially compared. So even though this model is not necessarily super robust, you can see the direction that we're going, sort of the advantage of this process. And so I want to come up here and mention one more thing, sort of before I end things. We also provide a script for doing this on multi-Radeon GPUs. To run this, we'll need to run it with Torch Run, which is why I'm not doing it in a Jupyter notebook. There's also, I recommend exploring the Accelerate library, the Hugging Face Accelerate library. And instead of doing Torch Run, you'll do Accelerate Launch. That sort of has its own parameters. You can set up YAMLs, so config files, right? Again, config files to set up your model and quantization and other things. But most of this is fairly similar for a single GPU. I also passed this quant storage because when we do what's called fully sharded data parallel, or FSDP, this is sort of a way for a multi-GPU setup to communicate its shards. It shards the data. So if you're keen on doing homework again, definitely FSDP is one of those keywords to write down. And so this is a stripped down version, and then anything commented is sort of what's changed. I have found that on Radeon, checkpointing your model as it trains throws an error, which I don't fully understand. It doesn't seem it doesn't seem quite to make sense to me. But I will be having some discussion on the GitHub repo. So I'm definitely interested in some reproducibility of this error. And then besides that, we also, in our training arguments, we also just pass specify for FSDP a full shard. And then auto wrap basically applies it to each sort of, again, if we think about a transformer model as having a bunch of different parts, it applies it. It trickles down essentially and applies it. And we can train this as well. Yeah, and then you can run it with Torch Run. So with all of that, so we hit single GPU and multi-GPU with FSDP. With all of that, I want to thank you for listening to me ramble for about an hour. Here are some other great resources, some ROCm blogs, which are quite relevant to what I spoke about today. You can hit up Fluid Numerics on all of the usual places, Reddit, GitHub, YouTube, LinkedIn, contact us on our site. And with that, with a little bit of time left, we will head into the Q&A.
Howdy.
Hello, Joe.
Let me dig through here. I got a couple questions that came in for you. Let's see. In cases where the model and dataset are too large for a single GPU, how well does Llama 3 scale on multiple Radeon GPUs? Do you recall if we actually got some of those figures in? Just
Yes.
looking at like the runtime for the fine tuning across multiple GPUs.
Yes. So, in my experience, the doing things on multi GPU does slightly increase performance in terms of time. I think a figure that I had was it took about 100 minutes on single GPU, and then I think it maybe took 80 on doing it across two. And then for
Okay.
Llama specifically, I think the memory footprint was maybe not quite what we wanted either. I cannot remember, unfortunately, specific figures for the memory footprint. But I would like to sort of interrupt myself and say an example of the sort of memory reduction that we have. Maybe a key thing that I should mention is that in practice, loading the Llama 3 8 billion. Today we were running on a Radeon Pro W7800, loading the 8 billion parameter model as single precision would not even fit on the GPU. But with quantization, training it, the training phase only required about 14 gigs of memory.
Okay. Yeah, and I mean, I think in terms of the imperfect scaling,
I'm sorry, Joe. I think you cut out a little bit.
yeah, all I'm saying is just that in our specific hardware could be part of the culprit in the imperfect scaling that we saw. The one of the GPU cards is sitting on an X4 PCI lane. We did get another question in from the chat.
Yes.
We'll see if we could do our best to answer this. Informative presentation. Thank you, Jeremy. A couple of questions was setting up PyTorch in ROCm. He has an AMD 5600 XT in Linux Ubuntu LTS 22. So Ubuntu 22. Okay. The errors generally were along the following lines. CMake required a newer version versus the one that came with my ROCm install. I got an error with a library called RockBlas LT. Tried GPT to debug it. Yeah, so I'm going to start off here. Do not go to ChatGPT to debug ROCm stuff. ChatGPT is always going to be months behind what is bleeding edge, and what you're doing is bleeding edge. You're working with software that is actively in development. ROCm is still fairly new, and expertise is growing online, but it's certainly not fully grown. So be careful with getting help from ChatGPT. Let me finish reading this. ChatGPT wasn't useful. Surprise, surprise. I wanted to run Whisper AI on my Radeon card. Would love your input on this. Garrett, do you have any comment on that?
Off the top of my head, I do not know what the architecture is for 5600. I don't know if you can recall, Joe. But I do not think it's GFX 1100.
No, it's not. But this sounds like there wasn't a particular issue with the GPU card compatibility. It sounded more like a CMake requirement. So CMake doesn't come with ROCm, right? CMake, you can just apt install CMake, or you can build CMake from source. I mean, for those of you who don't like building stuff from source, there's a great resource called SPAC. That's SPACK. SPAC is a package manager that will install packages from source code. Highly recommend using it, especially if you want selected versions of things like CMake and even other scientific libraries. When you install, I'll go through the usual things you want to do. As Garrett mentioned, make sure your GPU is on the supported list. That's the way to make sure you're going to have an easy experience. If it's not, your mileage may vary. We have some unsupported GPUs that we use. We know they work now, but you got to do some quirky things to get them to work sometimes.
Yeah. If I can add anything to that as well, I'll say that ROCm does not necessarily come with the full suite of ROCm libraries installed. I know there are other things like RockThrust. I believe RockBlas LT is not necessarily installed by default. There's a few other ROCm libraries which may be required for, especially the machine learning AI stuff, which you may need to look up as well.
Yeah. So As of 6.2, ROCm 6.2, if you're using the AMD GPU install script, which is one of the possible ways you can go about installing on Ubuntu, using the ROCm use case should get you everything. If it is missing, you can just apt-get install ROCm-hip BLOS LT, and that'll clean you up there. We do have another question that came in. What multiple Radeon W7900 setup would you recommend for training with LLMs requiring more than 48 gigabytes of VRAM?
I don't know if I fully understand the recommendation being sought here. I would definitely you mentioned W7900.
Mm-hmm.
Those are what I would look at. Compare for greater than 48 gigs of memory, because the W7800 and the W7900, I believe, both have 32 gigs of RAM per card. So that's one way of reaching above that 48 mark. Compared to, I believe, maybe the 7900 XTX, which has 24 gigs of RAM. So not in the Pro line, but in the consumer line. So I guess that 7900 is where you're getting the 48 gig maximum. But
yeah, I mean, in terms of like motherboard to go with that, if you were to do Radeon Pro W7900, minimum requirement, make sure, don't make the mistake that I did, get a board that has at least 2 slots, PCI version 4, 2 slots that are 16 lane. Some of them will have 16 lane slots, so they're physically, you can plug in a 16 lane card into, but the secondary slots will not actually support by 16 bandwidth. So just make sure when you're doing that, I don't want to make any plugs for specific vendors here today, but when you're looking at boards, just make sure you get PCI v4 and that multiple slots will support 16 lanes. So that's also making sure you have a compatible CPU to go with it. On that note, I will say the AMD's the 7900, the Epic Threadripper 7900 series will support multiple lanes with PCIe v4. So just use that information accordingly. If you do have questions, you can always, again, reach out to us, support@fluidnumerics.com, find us on Reddit, whatever. We'll be happy to answer those there. We got another one from Stefan. Do you have any experience parallelizing Radeon GPUs on more than one workstation? For example, 2 Radeons on one motherboard and one on another, communicating over a LAN network.
Flat out, I do not have experience doing this, but I can tell you where to look, and that is in the Hugging Face documentation. I believe they do have some. If you look at the documentation for fully sharded data parallel, so FSDP, there are subsections somewhere in that documentation for multi-node setups.
I think there's a hint towards packing as many GPUs on a node as you can, simply because it's a little bit easier to do, and you get better scaling when you're doing on-node only communications than when you have to cross a network. So there's definitely a focus to cramming as much as you can on one system. But yeah, I think Garrett's spot on. FSDP documentation would be the place to go, and it's certainly something that we're going to be looking at building out in some of these webinars coming up in the next year. So Good question. Thank you, Stefan. That I don't see any more rolling in at the moment, but as usual, it's been a pleasure hanging out with you all for an hour. Garrett, thanks a lot for the presentation. Do you have any final words before we go?
Check out the GitHub repository. All of the links from this webinar and the previous webinar are in there. Please play around with it and break things, and let us know what breaks.
Yeah. So I'll underscore those, all the slides if you want those. Check out the AMD ML examples repository.
Yes,
so it's github.com/fluidnumerics AMD ML examples. All the slides, everything are available there, and I believe the hosts of this event at AMD have also shared links to the previous webinars, so you can catch up on any material you may have missed. Thanks, y'all, for joining. We'll catch you at the next one sometime next year.
Thank you all so much.